Good morning, and welcome to the second in the series of talks during the intensive session. The seminar coordinator, Cristobal Carambo, will introduce today's speaker. Cristobal?
Good morning, everyone. Just to introduce, Jordan Peccia is the Thomas E. Golden Jr. Professor of Environmental Engineering and the Director of Environmental Engineering Undergraduate Studies at Yale University. Jordan earned his PhD in environmental engineering from the University of Colorado. His research mixes genetics with engineering to study childhood exposure to bacteria, fungi, and viruses in buildings. Jordan is a member of the Connecticut Academy of Science and Engineering and associate editor of the journal Indoor Air. He is leading the seminar on solving environmental problems through engineering. The title of his talk today is The Next Generation's Environment.
I hope you can all hear me okay, and I hope you can see this chalkboard well. Thank you very much for that introduction, Cristobal, and also thank you to Jim and Stephanie again for all of your efforts in organizing this fantastic intensive session for the Teachers Institute. It's really my pleasure to get to talk to you today, and I spend a lot of my time in research trying to solve environmental problems, but I spend also a decent fraction teaching. And I'd like to share with you some of my perspectives between the two. That is, solving environmental problems and how our next generation, or the students that we're teaching today, are going to need to solve those problems and how they're going to need to act and interpret the world as we move forward and make progress. So you're looking at the board here. Some of you may like this, some of you may not like this. As an engineer, this is pretty standard stuff, and you get used to it and you get really pretty comfortable with it. In fact, it doesn't look complicated at all to me. It's just enzyme kinetics. In fact, it's a simplification of a microbe. We're just calling them, you can see maybe here, cells are a bag of enzymes, right? If this isn't complicated to me, one thing I will tell you is complicated, and I think we all can agree on that, and that is people are complicated. So I want to talk a little bit about the intersection between engineering and people today, and we'll talk about that through the lens of the environment. So what is engineering? Well, the first thing to note is that science and engineering are simply not the same. They are different types of disciplines. Science is the systematic study of physical and the natural world through observation and through experiment. Engineering is the application of science, and we apply it for some specific reasons. That's to solve problems and to design things and to build things, right? And we build a lot, right? We have built water treatment plants throughout the United States and throughout the world. We treat billions of gallons of drinking water and billions of gallons of wastewater successfully every day, right? You can look at this as just maybe the brute force sort of engineering, right? We have a problem with climate change. Let's not worry about anything else. Let's just build a great big factory that's like a vacuum cleaner, and it sucks air through it, removes the carbon dioxide, and puts low carbon dioxide air back out into the atmosphere. We do crazy stuff like that too. And to be an engineer, you really need to get in touch with your rational side. And we should have a discussion about whether people are rational or not, and what the rational side can get us. This is the Amiens Cathedral in France. This is my favorite cathedral, and I'm a great lover of large cathedrals. It's high. It's one of the highest ones, and in fact, John the Baptist's head is supposed to be buried in the vault, although I don't have any confirmation about that. But the striking feature of this cathedral is its height, right? And the people at the time that this cathedral was made, as Gothic in design and architecture, wanted the vaulted ceiling to get as high as it could so it could reach the heavens. And that's probably not a rational thought that they were going to reach the heavens. It's more of a spiritual thought. But it took some rationality to get that vaulted ceiling very high. It took somebody to understand that vaulted ceilings can be heavy, and that when you have columns that are long and thin, they start to buckle under that amount of weight. And that you could load it in an eccentric way, and you could push the load to the exterior of the building so it would buckle outward, and then you could buttress that buckling, right? Those are rational approaches to getting toward maybe a spiritual outcome. Here's another example. I don't know what you would be thinking if you landed on the moon and you stepped out and this was the view that you were greeted by. I think some people say that they've thought, about their existence in the world. They thought about the vastness of the universe, that we weren't maybe alone, that the earth is beautiful. I think that I'd be thinking about how in the hell am I going to get home? It's 240,000 miles between the moon and the earth. We have to have enough fuel. We have to have the right technology to blast back off of that moon. We have to hit the earth just right. We have to go through the atmosphere without burning up. We have to land somewhere around Florida. I would be hopeful in this case for a rational engineer or group of engineers that have designed systems that work. At some point, we can talk about what's true and what's not true, but in other cases, things just need to work. So this is what engineering models look like. They can be for anything about a rocket's trajectory to not burn up in the atmosphere and to get back to Earth. Or they can be something like the infectious disease transmission. This is some different models for dose response for different types of infectious disease. It could be in water, could also be in air. Now the model at the bottom says something about the transport through the atmosphere. Again, these are rational approaches. I want to share with you a YouTube video that a colleague of mine sent today. This is a mannequin emitting a fluorescent fluid, so it's visible. The droplets in this mannequin are about the same size of droplets that are talked about so much with COVID transmission. This is a basic surgical mask, and the mannequin is coughing at a volume and velocity that's typical for humans. Watch now what happens when they take the mask off. And then here's now a more effective mask, not with a perfect fit, but a more effective mask. This is an N95 with not a great fit. All right. The point I wanted to bring home there is the following. That's a rational approach for looking at things. And you can come to a pretty simple conclusion there is a mask helps. You should wear a mask. It doesn't matter what you think about the Constitution or personal freedoms, wearing a mask is going to reduce emissions from a person. It also can be pretty insightful here, like don't stand behind a person wearing a loose-fitting mask, right? And if we kept on going with that video, you would see a close-fitting mask can do a lot to reduce emissions. All right, so I want to go on and take this kind of topic and this idea about rational design and for the world into a few different areas, and these are areas that our seminar is discussing. Let's first start with water. Water treatment has worked very well in the United States and many parts of the developed world, right? We live longer in a large part due to our ability to treat drinking water. Okay, so this plot shows the increase in filtered water population. This is population that was being served treated drinking water, and the reduction in death rate from typhoid. Same thing here, but now it's showing chlorination. Chlorination began, I think this is in Philadelphia in 1909, and again, you can see the drop in typhoid fever. Typhoid fever isn't something that we worry about very much right now anymore in this country, and there's a whole host of organisms and diseases we don't worry about. Your chance of dying of an infectious disease used to be much greater than your chance of dying of cancer. And now that has switched significantly. Beyond antibiotics and that development, the greatest increase in life expectancy in the United States came from the treatment of potable water, right? And so I want to give you a modern day example where we're learning new things through sewage. So this is some work from my lab where we're trying to track the coronavirus outbreak through sampling sewage for the virus. Right? The idea here is instead of testing 200,000 people in the New Haven area, we can test the wastewater. Everybody poops. They provide a sample that goes directly to a wastewater treatment plant where it can be mixed and in some cases concentrated. If we can get a sample of that and get the concentration of COVID, one sample, which costs about $40, could tell us something about how many cases there are in the area, or at least or how the cases are looking in that area. The reasons for doing this is mostly because testing is difficult, and we know that it takes time for test results to come out. Testing is often prompted by symptoms, which are usually 5, 6, 7 days into your infection, whereas you may be shedding well before that. And then there's all the asymptomatic cases that never get tested by testing that also may be shed in wastewater. When we do that, you can see this graph on the bottom. This is just a linear plot. This is a log plot, so it's the same data, but different ways of looking at it. Let's look at the log plot. You can see this a little better, but you can see the outbreak come up. You can see it peak, and then you can go back down. You see the same type of behavior in testing data, but the difference is our data shows up on average about 7 days earlier. That is, if you put a smoothed curve of our RNA data versus a smooth curve of the case data, and you look at the differences in the peaks or the deltas in the two performances, the RNA data shows up 7 days earlier, suggesting that wastewater indications of SARS-CoV-2 could be a 7-day leading indicator. Another kind of example of wastewater or drinking water treatment is the fact that we treat our drinking water very well in many parts of the world, right? We're now not just filtering it, we just don't throw chlorine in the water. We do advanced processes where we flocculate, we wrap, mix, and coagulate, we do sedimentation, filtration, and then sometimes many different ways in between. We have complex design for flat sand filters where we can remove organic contaminants. We can do reverse osmosis. We can treat seawater to drinking water levels. We can do processes called forward osmosis that save in the energy application of that. We can do a lot with drinking water, but we're certainly not perfect. This is lead poisoning in Flint, and I know a lot of you are aware of that outbreak that occurred in Flint, and that little blip here is the outbreak, right? That is to say that certainly there was an increase in the blood lead levels of children because of mismanagement of the drinking water system in Flint. But I also want to show you the rest of the curve. What was happening before 2014? Look at the blood lead levels then. So this is above 5 micrograms per deciliter. This is considered sort of an unsafe dose for children. And by the time 2014 rolled around, there was only about 5% of the children that had lead levels that high, and then it bumped up to 7 or 8% during the problem with the water system. But even 20 years before that, it was up to 50%, right? That's because somebody had talked us into putting lead in paint and painting every interior surface in our home with it. They'd also talked us into putting lead into gasoline and combusting that gasoline and aerosolizing it around the environment for the last, 70 years. And so the blood lead levels of people prior to Flint had always been significantly higher. To be sure, Flint was a big problem. The biggest issue here was just people lied and were negligent in their duties. But drinking water levels in the United States have not been such a problem. That's an example of an issue that has been cropping up, and we still know that we had lead problems along the United States based on a legacy of lead pipes. But around the world, the problems are much more severe, right? In many parts of the world, less than 50% have access to clean water. That is, access to water that doesn't have infectious pathogens in it, water that has been treated somehow has been deemed safe, right? Much of that is in some areas of South America, Southeast Asia, and Sub-Saharan Africa. There are technologies, to be sure, to try and help locations and villages that are not economically developed enough to build water treatment systems or modern water treatment systems like we have in the US and Europe and Australia and different parts of Asia. There's things like ceramic pots that can filter the water. There are solar disinfection technologies. There's something we talked about briefly in our seminar, the 3-pot method, where we settle microorganisms down and then can use those. But those are certainly imperfect methods. There's also building infrastructure that's rapidly developing across the world. But I think what we have to consider with all of these types of cases is how do we implement that infrastructure across the world? If you're a young student right now in high school or in college and you're engineering and you're interested in water and wastewater, chances are that you're not interested in providing clean water for the municipality of Wichita, Kansas, right? You are interested in going to sub-Saharan Africa and solving water quality problems. The easy part here is the engineering. It's the design of concrete. We know how to make a tank. We know how to dig holes. We know how to pour concrete. We know how to do all of that stuff. We know how to provide clean water. But the difficulty there is going to be working with communities that are very different than you and finding ways to work together and to communicate well for an overall goal. In fact, in the work that we've done in Tanzania, we've thought about a more holistic view of treating water in some of these villages. This is a case where we're doing a water improvement of a pond for agriculture, but we're thinking holistically about the entire village and what we call sort of an overall water poverty metric. And there's 5 parts to this. One is, are they using the borehole or rainwater? These are the clean water sources in the village. What's the water quality that people are using in general? How far does a person have to walk to get to a water source? What's the time used and spent in collecting water, and what's the cost of the water? Now, in a perfect situation, and certainly in the situation that I wager almost all of us live under, we're 5 stars. We're out here at excellent in every case. We're not so bad here and here, but here we have big problems, right? And the problem here is with girls. Girls are the ones who have to walk to gather water. They're the ones who have to spend long times gathering waters, and they do so at the expense of their education. This isn't something that engineers are taught in the United States, to worry about a young woman's education. But it's something that we certainly need to be thinking about if we're going to solve environmental problems. We can do the technology, but we need to be more engaged in these types of social issues, right? It's not just small villages that are undeveloped that have a problem in the world with water. It's cities. In fact, a lot of the action is in cities. 2/3 of the whole world population is going to live in cities by 2050. And look at the growth rates of some of these cities across the world. Lima, Peru is at 15%. Karachi's at 34%. Lagos is above 36%. Cairo, 26%. These cities are exploding, and their infrastructure is absolutely not keeping up with the population. The infrastructure wasn't sufficient for the population to begin with. Let's look at an example of one of my favorite cities. This is Lima, Peru. Lima is just an extraordinary place. I really love the city. I love the food. I love the environment. I love everything about Lima. It looks pretty nice here too, right? You go running along this boulevard. It's great. You can get some really great food in all the restaurants around this area called Miraflores. There's lots of nice hotels. There's a Ritz-Carlton over here you can stay in. But this is not the experience of everybody who lives in Lima, right? More than 1 million people in Lima live in areas like this, right? That have been pushed up into the mountains. These are people that have been moved from rural areas to Lima to looking for opportunities, can't afford land, can't afford new housing, and are forced to live in these types of conditions. So what is the water and sanitation system here looking like, right? You can see by the fact that there's all building materials, there's a lot of garbage and waste around, that they don't have daily waste pickup. They barely have roads in these areas because they've been pushed high into the mountains. This is a water tank, right? And you can see maybe a few lines coming out here and pipes that might go to a few different houses. They don't have toilets. They don't have plumbing. They don't have anything that they can flush. In some cases, they have some latrines. In a lot of cases, there's just open defecation in this area. Again, less than 10 miles from a Ritz-Carlton. Now, around the world, the situation is not so different. This is in sub-Saharan Africa, but we're divided into lots of different areas between least and most developed. This is the situation in Europe and North America. Green is good, yellow is bad. And this is sanitation services, right? Whether you have a nice toilet, whether you have an outhouse, or whether you practice open defecation. And you can see that it's uneven across the world, that there are problems in urban areas, but the problems in rural areas might be more significant, right? 4 out of 10 people in 2017 used a very safely managed sanitation service, like the ones that you and I have. That means 6 out of 10 need improvements in this area throughout the world. Again, we teach engineers a lot. We teach our students a lot. We teach them an awful lot about how to design modern systems. They know the chemistry, the math, the biology underpinning this. They take a core curriculum in humanities, but I'm not sure anything prepares them for dealing with cultural barriers for and against open defecation. All right, air pollution. Let's move on. So the news of air pollution in many parts of the world is pretty good, right? Let's take the United States for an example. Our gross domestic product has been up 150% since 1980. We travel way more vehicle miles since we did in 1980, right? Our population's increased, we consume more energy, and our CO2 used to increase, but now it's kind of gone down. Some of this was the economic downturn, some of this is savings, but it's still been up since 1980. Through all of that hammering on our economy and our environment and the growth that's occurred with that, we have decreased the 6 most common aggregate air pollution metrics by almost 70%. It's mostly good news. This was Los Angeles in 1968. This is Los Angeles in 2005. To be sure, they still have problems. This is Beijing, China now in 2010. And there are many cities across the world that look like this. And so, again, while we may enjoy some of those benefits, New York City is certainly much cleaner in terms of air quality than it was in 1970. It's uneven across the world. We do have problems still in the United States. Los Angeles, Houston are the biggest problems. This is for ozone levels. We see this in Europe as well, but we also see these in a lot of these rapidly growing areas. Lagos, Karachi, Mumbai, Kolkata, Bangkok, Beijing, Tokyo as well. I guess Tokyo is not rapidly growing. Right? Air quality and poor air quality is responsible for up to 8 million excess deaths a year. An excess death isn't a death where somebody was killed instantaneously. It's a person who wouldn't have died that year if they hadn't been exposed to that poor air quality. These are often people with poor health or people who are older, who suffer cardio or respiratory syndrome symptoms and end up dying in a hospital. And these are associated with days or areas that they have bad air quality. In the United States, the estimates are that there's 200,000 premature deaths from poor air quality every year. Compare that with what? We're now at 130,000 deaths from COVID, 60,000 deaths from the flu, 40,000 deaths from gun violence. Certainly air pollution, even though it's better, is still a significant problem in the United States, right? It's worse in the most industrial and urbanized areas of the country as well, although geography plays a role in this too. All right, and so what have we done in response to this lately? Well, you know, a lot of the air quality problems, especially PM 2.5, comes from traffic and it comes from car and emissions from tailpipes as well as cars. One thing you could do is you could just burn less fuel per mile, or you could increase your fuel efficiency. Lots of countries have done this. This is the fuel efficiency for different fleets of cars in different countries. Contrary to a popular belief, all cars are not the same. The cars we drive in the United States are not the same as cars that are driven in Japan or Europe or South Korea or even sometimes Mexico. And in fact, the United States lags behind, significantly far behind in fuel efficiency and economy. Now that was fixed or supposed to be fixed under Obama-era regulations that I think were passed in 2010 and 2011. They weren't passed. It wasn't congressional, but it was an executive order to increase the fuel efficiency of cars by 2025 to 56.2 miles per gallon, right? That seems high, but of course, Europe's going to be at 60, Japan's going to be at 55. Canada had the same goal as well. And we're well on our way to that, right? Although we stopped right about here. Well, I guess we're almost at 2020. And so the US and Canada we're well on their way to making that, but we stopped that. The current political situation decided that we didn't need those rules, even though the car companies like Ford Motor Company didn't want to get rid of the rules. They were against rescinding this. We stopped it anyway. And I would say in the future, you know, we need engineers that work at places like Ford Motor Company that should say, I'm not doing this. I am not going to design a car that isn't fuel efficient. And I get these crazy ideas from my students. one time I suggested a project on some sort of refining type project that worked with fossil fuels. And I remember 2 or 3 students of mine just said, let's not do this. Let's do something else. I don't want to have anything to do with fossil fuels. I don't want to think about fossil fuels. I don't want it to be any part of my life. That's a bit extreme. But again, I think that if we have students that have a consciousness and say, you know, I'm just not going to work on the problem. We know what the problem here is, and we know that there's technology that can solve that problem. We need to teach our students to stand up and to, you know, in these cases, do what's actually, in this case, pretty rational. Indoor air pollution is also a big problem. In fact, the quality of indoor air is usually worse than the quality of outdoor air. That's because we have a lot of sources inside and we don't ventilate our buildings very well. And we're getting worse at ventilating buildings because we're trying to save more energy. Here's one that strikes home to all of us as teachers, carbon dioxide. So carbon dioxide has some neurological properties that are not great for us. And when you're exposed to high concentrations of carbon dioxide, you can lose some neurological function. They do these types of experiments where they have volunteers take tests and they pump carbon dioxide into that room. And then they do it at different levels and they grade the tests on things like breadth of approach, information usage, initiative, task orientation, focus activity, applied activity, the types of things that would be important for taking tests. Now they find that when the carbon dioxide concentration is low, about 600 ppm, so atmospheric carbon dioxide concentration right now is around 400, 410 ppm. In a building, people emit carbon dioxide, and so the concentrations go up a little bit. I'm a weird, so I monitor the carbon dioxide in my basement and living room, and it's around 500, 450 right now. But in a classroom, you often have a poorly ventilated space, and you often have a lot of emitters of carbon dioxide. Each student is continually emitting carbon dioxide. Those concentrations very commonly go above 3,000 parts per million, and certainly are often between 2,000 and 500 parts per million. And now you're on this black line. And so your students are in a situation where they can marginally perform basic activities. They're in the dysfunctional area of initiative. They have problems with information units. They have breadth of approach problems. In fact, when people who are drunk take these tests, they get about the similar results as somebody who is exposed to 2,500 ppm carbon dioxide. Now, there are different levels of drunk, and so this is just the level that would disallow you from driving a car. All right. So, climate change, science in mitigation and impacts. We shouldn't be arguing anymore about whether climate change is occurring. Certainly, we know that the world is getting hotter, and we know that many of those inputs are man-made. I think a lot of you have seen this animation from NASA, but again, red is above normal, blue is below normal, and then you can see as we go forward in time, the Earth gets redder and redder and redder. Warming most at the poles. So certainly temperature and carbon dioxide swings have occurred many, many times before. I mean, if you look at the deep history of our Earth, of course, it has changed significantly. But in the last 800,000 years, we've never really gone above 300 ppm, and now we're at 400, right? So this is something unique that is occurring right now, even based on geological records. Sea ice is melting. This is a bad thing, right? And it's a bad thing because as sea ice melts, we don't get reflection of solar radiation back into the atmosphere. That heat gets absorbed into the ocean. And when it gets absorbed back into the ocean, it heats up the Earth even faster. And so you get this sort of combined effect, or what we call the feedback loop. Our students need to be good at looking at data. So you can see that this data is going down, but it doesn't go down every year. Right? It goes down in an irregular way. There's some good years, there's some bad years. And so the better we get at teaching our students how to look at trends and how to look at complex information and data, the better our students are going to be able to figure out things in the future. So we talk a lot about mathematical modeling and engineering, and in our unit, we just talked really briefly about what an energy balance on Earth would look like and how you can pull a temperature out of that energy balance and adjust for different levels of carbon dioxide. And that's just exactly what scientists have been doing, trying to model the future. They look at different types of scenarios. This is the degrees Celsius warming above or below based on different scenarios of carbon use and carbon dioxide produced over time. You can see if we do nothing, we warm very rapidly by 2100. If we do a lot, we warm very little. Again, the blue scenario is doing a lot. That can keep our sea ice at least extent a little bit from what it naturally was, but we're going to get rid of our sea ice between 2050 and 2100 if we don't do anything. We're also going to change the pH of our ocean. It's going to become more acidic from carbon dioxide. All right. We have some other tools, and these are tools really of modern engineering. These are tools that I was not taught. These were certainly tools that the generation of engineers before me were not taught. We were taught to sort of dominate over nature, to build things, to be a little bit patronizing about it, and to, we know better. Technology can always solve things. A colleague of mine who's now retired used to say, I don't like any of this natural stuff. You've never seen a supersonic bird, have you? All right. But we know now that we've caused a lot of problems by some of our previous solutions. And so we have principles now. We have part of our engineering design where we start thinking about ways to prevent problems and to design things that not only solve one specific problem, but don't cause another problem. Right? To look into the future to do that. These are principles in green chemistry. These are principles in green engineering. That got inserted incorrectly, so I'm going to keep on going. We have a tool like life cycle assessment, right? So life cycle assessment sort of looks at the whole picture from cradle to grave of the youth. And what you're looking at is a graph here of greenhouse gas emissions in CO2 equivalents per megajoule of energy. And this is for the production of syngas. It's a different type of fuel that can be used even in combustion. And so it's greenhouse gas produced per unit of energy produced. Here's making syngas from fossil fuels, from natural gas. So you make about this much greenhouse gas. This is by making syngas from algae. So algae are supposed to be more sustainable because they're grown, the energy comes from the sun, and then you can burn those or you can refine them in a way to make a fuel. But it turns out that if you, in your refining process, use a thermal drying, right, and you run that thing by a fossil fuel, your thermal dryers, you're going to make way more greenhouse gas than you would if you just did fossil fuel. But if you use solar drying or solar assisted drying, then you can get far under and you can make a more sustainable fuel than a fossil fuel by using those types of techniques. We can apply this life cycle assessment to many, many different areas and try and get some estimates about whether the process that we're producing really is better for the environment, right? We think about things in terms of risk right now, and it's important for our engineers that are being trained right now to think about context with all that they're doing, right? This is your life expectancy in the United States, or a loss of life expectancy in the United States based on days from the fact that there's contamination in drinking water. There's a bar there, but it's pretty small. On average, it's a couple days. Here's from indoor air pollution. It's significantly higher, but you can't see that here because the scale is such that they're both squished down. But again, it's only like 10, 20 days you live less because of indoor air pollution. Now, these are things that you may or may not be able to control: drinking water contamination and even indoor air pollution, certainly outdoor air pollution. These are things that we think about that happen to us, and we have a low threshold for risk here. But driving a car gives us some benefit, and we have a higher threshold to risk, and indeed, the risk is much higher, right? Being poor, none of us choose to do that, but that has a much higher risk and daily days lost in a lifetime. Smoking, being 30% overweight. Then, of course, I think everyone, this is pretty obvious. An unmarried male just does not usually contain a lot of practices. What I think about sometimes is as we develop and we train different engineers, and if an engineer, a young engineer, ends up at a city, at a Board of Health meeting like I attended last night, and there's a concern about, say, 2 million gallons of sewage just were spilled in Hamden, Connecticut right now in the last couple of days. It was a couple blocks from my house. It went into the Mill River and it's gone into the Sound now. people are concerned about that. What's on the mind of an engineer who knows that and knows that the risk is really going to be relatively small, right? But they think about all these people who drove a car to the meeting, or people who maybe have a box of cigarettes in their pocket when they're talking about the risk of water contamination in the meeting. People are complex and systems are complex, and we have to have a lot more interaction, I think, with humanities for engineers to be successful. And so my last slide here is thinking about what our next generation will need to solve today's and our future environmental problems. They absolutely need to be rational. We have frameworks for this, we have engineering systems, and these systems work, and they're continually getting better and better. We're good at that. But there's more things that they need to be, and these are things that we typically haven't thought about, but we need to be thinking about, not just at my level of undergraduate and graduate teaching, but certainly in high schools, but in junior highs and in grade schools as well, right? We need to make sure that engineers look like and are able to communicate the populations which we serve. If you go and you look for some icon of an engineer on the web, you're always going to find something that looks like that, right? Our engineers need to be citizens of the world, right? They need to travel, they need to speak other languages, they need to be able to interact with other people. As I said before, if our engineers have the desire that are trained in the United States to solve the water problems of the world, they are going to be working outside of this country, and they need to be prepared to be able to do that. They need to be able to operate in a world that does not necessarily always value truth and rationality, right? For better or for worse, humans are complex. Our news cycle is disastrous right now, and they need to be able to operate in a world where people talk about ideas like my truth instead of the truth. And then finally, they need to learn to design systems and solutions that don't result in new problems. That's it. That's my email address, but I think you all know how to get a hold of me, and I'm happy to answer any questions. And I've also sent a copy of the talk to Stephanie.
Thank you very much, Jordan. I'm going to start the Q&A with a couple of questions that have been posted into the chat, but I'm also encouraging everyone to join in with your own questions whenever the need arises, okay? So my first question is coming from Virginia Redwine Johnson, and she says, given the fact that there are so few members from underrepresented groups in engineering, how do we encourage more engineers of color or minority groups and women to start their engineering careers early?
That's something that we talked a little bit about in our seminar, and I also think that that's something that I observe at a university, because by the time students get to me, right, the pool has already been adjusted. It's already been changed. Now, there are certainly things that we can do at a university to encourage that and to make it a more welcoming place. But it has to start early in life. We know that for girls, right, there's evidence that shows by the time they're 6 or 7 years old, they've gotten the message, right, that girls don't do technical things, right? And so we have to start early on in childhood. As far as, I would say just a broad solution here, or a broad sort of expression, and I'm really actually more curious to hear what other people think about this problem, is that, it's my continual observation, especially working with a lot of women in my lab, in my major, that engineering, was built, it was designed by men, for men, right? That's the history of it. When I took a statics and dynamics or structural class in high school, I remember one of the problems was about a jack. And you were jacking up a car, and you're worrying whether the car was going to be too heavy and the jack was going to break and buckle. And we had to analyze the structure of the jack and figure out whether it was going to break, right? And I remember some people had, a girl in our class, a friend of mine, a woman, had a question about this. And the instructor said, haven't you ever jacked up a car before? And of course, I think most of the men in the class had done that, and their fathers or parents had made an explicit sort of, task to teach them how to do that, but they hadn't taught their daughters how to do that, right? And you just see this occur over and over and over again. The type of pedagogy, the way that it's taught at universities is still mostly taught sort of that engineering is a man's world. I teach at a university that has been around for more than 300 years. In the School of Engineering that's been around for more than 150 years, there have been about 3 or 4 different women tenured in that whole history, completely, right? And so we have a long ways to go.
Okay, I'll ask a question from Ryan. It pertains to your research on COVID and wastewater. He wants to know, why hasn't the rest of the country invested in data from wastewater like it's being done in Connecticut? And a follow-up question from Sally is that, how do you remove COVID from the wastewater once you find it there?
So the country is doing some investment on COVID and wastewater right now, right? And I think it moves pretty slowly. Testing moved fast, but there are no edicts from public health to say that you have to do wastewater testing, right? Where wastewater testing will help is in 2 areas. The first is, it's helpful here in Connecticut, and again, I interact with the city officials on this a lot because they have to constantly make decisions about whether things are opening and whether things are closing. When they saw the protests here initially, they looked around, they saw a lot of people without masks, crowds, and they were worried about that, right? And so the wastewater testing gives them something else to look at to see if there's a problem, and if we can see earlier, a little bit into the future, it's helpful. But all the resources, all the investment, all the public health apparatus right now has gone into testing. And while some areas of the country are okay with testing, I mean, areas like Arizona, Florida are kind of back on their heels in terms of testing. They're struggling to keep up right now. And so it's kind of hard for a city to say, well, let's also get together and test our wastewater. Phoenix doesn't have a Department of Public Health. So that's a problem. In terms of the COVID and the wastewater, there's a strange thing about this virus, as far as anyone knows, that is that it is there's a lot of concentration in stool, but nobody's ever been able to to culture an infective viral particle from stool, right? So we know the RNA is there. We assume, though, that most of it's not infectious in the wastewater. Even if it was, a lot of it gets removed in a treatment plant, or most treatment plants now chlorinate, and so by the time it makes it to the environment, it's been inactivated. I would think that the risk of getting COVID from wastewater is very, 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 very small.
Terrific, thank you. From Ricardo Moreno, regarding your conversation about CO2 in the classroom, he asked, as school teachers, what strategies are there to monitor the levels of carbon dioxide in our classrooms?
It's a good question, and I do it for all of my classrooms. You can buy real-time carbon dioxide monitors. They are less than $50, and you can put them in your classroom, and you can see what the carbon dioxide concentrations are. You may or may not have the tools to try and reduce that. You can reduce that, obviously, by opening up a window. You can reduce that by having good, strong ventilation in your classroom. But I'm fully aware that that's not available to everybody. What I would say is I would get one of these monitors. You can buy them on Amazon. They're not very expensive. And I would monitor it. And if it gets above 2,000 ppm, you likely have a problem, and I would talk to your administrators about that. Email me, and I'll send you or your administrators all the scientific evidence to suggest that this is not good.
Terrific. This is from Luis regarding your work, or the work in different countries to affect their water supplies. He asked, how do you overcome sustainability challenges? What are they in those countries where you're helping to provide potable water?
I think, thanks for that question, Luis. I think that my experience has been that the challenges are not the technological challenges. The challenges are the cultural challenges. And I can think of different ways to help to overcome that. The first one is again, you know, not every American is great at going to a foreign country and interacting with people in a rural environment, right? Let's just say that. But some are, right? The team I work with has a civil engineer that works there, and he has maybe 45 years of experience of working in the developing world, and he knows what to do. And he sort of tempers the interaction, and he works out sort of, how we interact with the community in a constructive way. And I'm constantly impressed and learning from how he interacts with different cultures and how he leverages people from those cultures sort of be part of our team, and so that we can get a cohesive group interacting. A lot of efforts don't do that. And you can on one level say, people from Europe, the United States should not be going to Africa and trying to help with these types of systems. But I would disagree with that. There's a great need, and I don't think that in a lot of countries they have governments that can functionally operate and do that. And so in order to solve those problems, there's going to have to be some outside help. But I think you have to strongly implement systems where you can work with those communities in cooperative, respectful, culturally appropriate ways. That's the whole crux of the problem. It's never the technology. I mean, we're digging a hole, we're putting a bunch of soil together, we're packing it down. Civil engineering is really not that hard. We've been doing it for a long time. You can see ponds all over the United States, right? It's building a pond in rural Tanzania that's the problem.
Thank you, Jordan. This is from Thaisa. She asks, how effective are UVC germicidal lights, and could they be effective in sanitizing classrooms, or at least the materials in our classrooms?
That's a great question, Ty. I had my PhD project was on UV germicidal lights, and in this case it was for TB, and it was for people who worked, the AIDS epidemic was still going pretty hard, and in isolation wards where people were susceptible to all kinds of different diseases, it was important to have as clean of a room as possible. The trick is that there are two ways to set up a UV system. One is called upper level germicidal irradiation, and the other one is to stick UV into a ventilation duct. And the idea is the air in the room gets passed into the ventilation duct, and then it's treated as it passes through, and then it gets recirculated and it's fine, right? That's not always a great idea, putting things in a ventilation duct, because the air has to get into the ventilation duct, right? So if you're in a classroom and you have 3 students with COVID-19 and they're coughing, that air is going to go out into the room. Some of it's going to fall to the ground, get resuspended when people walk over it. The small particles are going to stay in the air. They are eventually going to get ventilated out of the room and through the ventilation ducts. Now, ventilation rates are something like, in a classroom, 3 to 5 air changes per hour. That is, every hour, the room air is changed 3 to 5 times, but because it's well mixed, it doesn't quite work that way. And in a lot of classrooms, air change rates are going to be like 1 per hour. In your home, the air exchange rate is probably 0.5 times per hour. So it takes 2 hours to change that. The point being is it takes a long time for the air in that room to get into that ventilation duct, right? And so what you want to do is you want to put the UV right in the room. And so there's these approaches called upper level irradiation, where in the corners they shine UV lights across the ceiling. And so you can think of like the upper quarter of the room air being purple with UV lights. You got to be careful about that, because UV causes cancer and it's going to destroy your students' eyes if they look at it, right? No problem there. They have louvers and things like that so you can't see them. But, I always worry about a student or somebody climbing up there and being curious. But there are upper level approaches to sort of help. The best thing you can do in a classroom is to try and ventilate that classroom as much as you can.
Thank you very much, Jordan. Are there any other questions from the group here? I have none in the chat room. I would encourage you to, if you have any other questions, to pose them directly to Jordan, please. So I do have one here um, from Ginger Lee. She asks, what type of organizations or sites do you recommend for elementary students for field trips or visitations? Likewise, what kind of partnerships could scaffold development in younger students of color and females?
I think that if you try to partner with your university, you'll find a lot of willing partners. If there is a university anywhere near you, I think that you will find a lot of opportunity there. Universities in general are also looking to partner with K through 12 institutions to try and, to try and, achieve some of the goals that I talked about, right? Making engineering more diverse and science more diverse, and to try and interact with students early on and get them excited about it. So I think that's the easiest thing to do. I would also say that, in relevant to some of the things I presented here, every city's got a wastewater and drinking water treatment plant, and they are typically very happy to give tours. The wastewater ones especially, because you can't do much to wastewater. Drinking water, sometimes they want to be a little more careful about.
We have one or two more questions. So this is from Catherine. Are there DIY, which is, I guess, do-it-yourself ventilation methods for teachers to use, given that districts are not giving us access to proper infrastructural building air ventilation? A lot of us work in buildings that are old and windowless, so we're scared about reopening without proper air ventilation.
I agree. And the question was are there DIY?
Yes.
I was going to ask that too, Cristobal. Like, what suggestions do you have for us with poor ventilation systems in our classrooms? We're having to go back, and with students in our classrooms, like, what can we do to help that situation?
So I'm going to say two things, right? The first thing I don't want you to get too discouraged by, because the second thing is better, right? The first thing is that's a nightmare scenario, right? I mean, a bunch of students that could be asymptomatic in a small space with no ventilation, talking, interacting, that's bad. Okay, here's what you can do though, okay? Engineers think about stuff like portable air filters and UV radiation in terms of effective ventilation units sometimes. And that means that you can ventilate something with no ventilation just by circulating air through a filter, right? And so if you can get one of these portable air cleaners with a HEPA filter, you don't need UV or anything fancy. It can be just your normal air filter that's got a HEPA filter on it though. You need that because viruses are small. And it's sized appropriately to your room. That will take care of kind of your, I would call it nominal ventilation needs.
Are those on Amazon, Jordan?
They are. They're really popular now because people in China really demanded the need for those because of air pollution inside. So just look for a portable air filter. Make sure it's sized appropriately for your room and it's got a HEPA filter.
HEPA.
Yep.
Okay.
And Jordan, will those air filters recycle the air sufficiently in an hour? I mean, do they recycle efficiently?
Absolutely, yeah. They will give you something like an effective 3, 4, 5 air changes per hour, depending on what their flow rate is and what the size of the rooms are.
Okay. All right, here's our last question from Ricardo Moreno. Given what you know about COVID, how optimistic or pessimistic are you about school openings in the fall? Are states like Florida and Texas facing a dire situation? I think you already sort of addressed this, but I would pose it again for you.
Yes. I tend to, this is just, an opinion. None of us can see the future. I think that in a state like Connecticut, New Jersey, New York, it's probably a good idea to open schools and to be very careful about it with testing, et cetera, because there are just no cases right now in Connecticut. We've had days in New Haven now with zero. In fact, the testing apparatus, I think, took a holiday over 4th of July and didn't even test for a few days because there were so few cases, right? That is very different than what's going on in Florida and Texas. And if you are, and in California, and if you are in a location where the cases are rising right now, then I think it is pretty dangerous and dicey to go back to school, especially given, when, if I think of Yale's going back to school, they're going to test everybody before they come in. They have ability to change ventilation systems, but they're only ventilating now with outdoor air. They're not recirculating everything. They're going to put HEPA filters in. They have signs all over in the elevator saying, don't face anybody and make sure you wear a mask. They are thinking about testing people every 3-4 days or something like that. They have an app where everyone's going to do contact tracing. And if they're sick, they have to check in every day. I don't have a fever, all that type of stuff. And even then, they're going to do a reduced schedule of classes. I just don't see schools having the resources to do that.
Yeah.
I just don't. And I don't worry about students very much. And I agree with all the stuff about the low symptoms in students. I worry a lot about teachers. And, the schools are a bomb, right? They have this location where everyone is close and interacting, right? You don't know if you're sick, if you're asymptomatic, and then you go home every day and spread it in the community, day after day. So I think schools can be controlled in areas where the COVID is low, and I recognize how important it is for students to be in school. But I think in places where the epidemic right now is increasing, I can't see how that's going to make anything better.
Okay. Well, thank you, everyone. We're close to 12 p.m. I would first like to thank Jordan for an extremely informative and insightful and provocative talk. And I'd like to thank all of you for your participation and your keen attention. I hope everyone has a wonderful pair of hours before your seminar meeting. And with that, I'd like to close the meeting for everyone. Thank you. Thank you, everyone.
Thank you.
Thank
Bye.
you.